The main result of this work is the decidability of substructural logics, commutative substructural logics with contraction that have a hypersequent calculus with the subformula property. I'll explain what all these terms mean, but to start off, when I say logic, what I mean here is a set of formulas, what's also called its theorems. For example, if you take classical propositional logic, it contains formulas, theorems like P or not P, and also some of the other formulas you see on the screen. The logic can be defined in various ways, for example, as a set of formulas that is valid on a class of structures, or via a proof calculus. A proof calculus is a formal object that generates derivations, that's the formal word for a formal proof, and true-risk theorems of the logic. One of the most important questions for a logic is whether it is decidable or not. That means if you give me a formula, can I efficiently decide if the formula belongs to the logic or not? Can I decide this? And it's natural to use a proof calculus for this purpose, and also, in fact, to compute upper bounds, complexity upper bounds. And in this talk, we will be talking about using the proof calculus for decidability. Gensen introduced a type of proof calculus called the sequent calculus. And let me start, in case you've not encountered this before, let me start by explaining the sequent calculus for intuitionistic logic. The sequent calculus here is simply a set of functions, what are called inference rules, whose inputs and output are sequents. A sequent, meanwhile, has the form x turns style A, as shown on the screen, where x multiset union x is a multiset and x union A is a multiset of formulas. Then a derivation is constructed starting from initial rules by applying the logical rules and the structural rules. The logical rules introduce a logical connective on the left hand side, that's the antecedent, or on the right hand side of the sequent at each step. For example, in the derivation that I've shown on the screen, you can see that it starts with this initial rule over here, and then disjunction is introduced on the right hand side. Here's implication left introduced here, and you proceed downwards, creating more and more complex sequence. The structural rules don't introduce logical connectives, but instead they play on the structure of the sequence. So for example, here you have two copies of A in the multiset on the left, and it becomes a single copy in the conclusion. To use the sequent calculus to say something about the logic, of course, you need a relationship between the two. And that's what the soundness and completeness theorem says, which says that you give me a formula A, if it is a theorem of intuitionistic logic, well, then the sequent containing that formula on the right is derivable, and vice versa. What makes the sequent calculus a powerful tool is when it has the subformula property. So, as does the sequent calculus for intuitionistic logic, where every formula, if you give me a sequent and you consider a derivation of the sequent x turns style A, that's where x turns style A is at the bottom, every formula in this derivation is a subformula of x union A. This is a significant restriction on the space of derivations, and you can contrast this perhaps with the Hilbert calculus, where arbitrary formulas can occur in the proof. And to see that this holds, it suffices to look at the form of the rules in the sequent calculus and observe that every formula in a premise would be a subformula of some formula in the conclusion. Of course, this doesn't hold if you have a rule like famously the cut rule, which violates this property, but I'm considering post-cut elimination. So there's a cut elimination result in the background which says that you can avoid rules that break this property. Great. So once you have a sequent calculus with a subformula property, you can do backward proof search, which means you can search for a derivation starting with the given sequent by applying the rules backwards. If it terminates, then you can see if inside this tree that you obtain, if you can find a derivation, then it is derivable, else it is not. So that sounds great. The problem is that for most logics of interest, there is not a sequent calculus with the subformula property. And this is what has motivated extensions, more expressive types of proof calculi, and in particular the hypersequent calculus, which will be of importance in this talk. But I'll talk about the hypersequent calculus in a moment. I want to first go on and talk about substructural logics. Substructural logic is one that lacks some of the structural rules of intuitionistic logic. For example, the weakening rule that we saw on the previous page, or the contraction rule. Also, I talked about a sequent as being a multiset on the left, and implicitly that builds in exchange and associativity. By using a different data structure, you can also remove these properties, and then you get a substructural logic. The sequent calculus for intuitionistic logic, therefore, we can look as coming from the full lembic calculus by the addition of exchange, contraction, and weakening. And therefore, we can talk about intuitionistic calculus as being FLECW. If I delete just the weakening rule from the intuitionistic calculus, I will get FLEC. I'll remind you once more of the structural rules. This is what I mean by the contraction rule, and this is what I mean by the weakening rule. There are in fact lots of substructural logics, because not only can you delete some of the structural rules, say from FLECW, because you can then add further axioms and rules for properties like linearity, weak excluded, middle, bounded width, and so on, and infinitely many other properties in fact. And consequently, the logical connectives of substructural logic can model a broad range of phenomena. And you can contrast this perhaps with classical logic, where the logical connectives model truth, or in intuitionistic logic, where they model constructibility. With substructural logics, many behaviors and specifications in computer science, in particular, can be described using these logics. For example, with respect to the full lembic calculus, if you add restricted contraction and restricted commutativity, you can model syntactic types of natural language, context-free grammars, linguistic phenomena. If you keep commutativity but put a restricted contraction, restricted weakening, then you're in the realm of linear logic and variance, computational and resource awareness logics. FLEC gives a refined account of implication, because the weakening rule has been eliminated, removed, and this falls into the realm of relevance logics. In fact, every axiomatic extension of FLEC plus linearity is known to be a fuzzy logic, with applications in fuzzy systems modeling. In fact, new applications appear all the time that use the lembic calculus with extensions of axioms, maybe language extensions of modality. You could think of the bunch logics, which combine the substructural logic with intuitionistic logic, leading in the direction of separation logics. And this vast number of different substructural logics, motivates the interest in general results. And it's in that context that we have this general decidability result for the commutative substructural logics with contraction that have the hypersequent calculus with the subformula property. Let's look at it via a diagram, the logics that we're talking about here. So here's some selected substructural logics. We can see these are ordered by subset containment, and so you have FLEC here, and here are extensions of FLEC by various axioms. Here are the known decidability and complexity results in this region of logics. Of course, we have intuitionistic logic here, and we have FLEW. FLEC was famously proved decidable by Kripke in 1959, and this work will show how his argument can be extended to new proof calculi to capture all of an infinitely many extensions of FLEC by various axioms and properties. There are some scattered results on extensions of FLEC decidability, which, for example, with the mingle axioms and mingle type axioms, which are shown over here. I should also mention that in the case of FLEC already, the complexity bounds are horrendous, in the sense of Urquhart showed roughly matching lower and upper bounds that are not primitive recursive. FLEC is not primitive recursive, but it is primitive recursive in the Ackermann function. To make sense of the logics that we're studying, it's helpful to consider which ones have a sequent calculus with subformula property, and those are all the ones in black where the existing results were known. There is, for hypersequent calculi with the subformula property, there is this scattered result in the presence also of the mingle, and our result shows how to extend Kripke's argument broadly to the large class of hypersequent substructural logics. Here's the calculus, sequent calculus for FLEC. I won't look at the details, but feel free to pause and have a look if you want to have the calculus rules in mind. Let me sketch the Kripke's argument and then show how it extends to hypersequent calculi. So Kripke says something like this. You give me a formula f. If it has a derivation, first of all, then it has an everywhere minimal derivation. And everywhere minimal derivation means that every subderivation has minimum height. There's an algorithm for computing the everywhere minimal derivation from a derivation, but I won't go into that. The second point I want to make is that FLEC has high preserving admissibility of contraction. That means that if you give me the premise of the contraction rule, which has been written here, then the conclusion can be obtained by proof transformation without increasing the height of the derivation. So if you combine items 1 and 2, what it says is if you start with an everywhere minimal derivation and you have some sequent S1 that is above S0, then it cannot be that S1 is contractible to S0, i.e. using contraction rules to obtain S0, because then Curry's lemma would imply a smaller derivation for S0, and that would violate the everywhere minimality assumption. So this relation of contractible, which I'm using this symbol to denote, you can check is a partial order. Well, step 4, we start generating the proof search tree. As I said, it's backward application of all possible rule instances. But we add a side condition. We omit rule instances whose premise would be contractible to an earlier element. So if you look at this diagram here, you have this is not a proof rule, right? Because we have applied all possible rule instances here, and this is coming from these last two premises are coming from the disjunction rule. But one of the premises is contractible to an earlier sequence, just this one over here, and therefore we omit this rule instance. It remains to prove termination of this algorithm. For then, as stated before, we can decide if f has a derivation by looking at the final proof search tree and determining if it contains a derivation as a subtree. So let's get on to the Kripke termination argument. If it does not terminate in the limit, we can say that the proof search tree has an infinite branch. By the subformula property, we know that every formula in every sequent on this branch is a subformula of f. So let's extract the infinite subsequence on this branch whose succedent is identical, some formula A. We recall that every sequence from a partially ordered set has a subsequence that is either descending, ascending, constant, or an antichain in the sense of the definitions here. Antichain meaning that every pair of elements is incomparable, cannot be compared in either direction. We have seen from the construction, the proof search construction, and that the star side condition, that ascending and constant subsequences have been ruled out. Therefore, this subsequence must contain a descending or antichain subsequence. And Kripke's lemma shows that no such descending antichain exists. Another way of seeing this result is by observing that since every formula in the proof is a subformula of f, that means that for every multiset xi in this sequence, you can it corresponds in a natural way to an n tuple, where n is the cardinality of the subformulas of F. And Dixon's lemma says that over the set of m tuples, there is no descending chain and no anti-chain. Kripke uses sledgehammer. If you're not familiar with this phrase, it means to use significance of force to carry out an action. And I say that because the argument ultimately depends very little on the actual rules of the calculus. After all, Kripke's lemma, or Dixon's lemma, applies to all sequences of sequence or n-tuples, irrespective of how they were generated. So it's enticing to ask, can we then extend these arguments to other logics where the rules are different? Unfortunately, the big limiting factor is that most logics do not have a sequent calculus with a subformula property. And that's where the hypersequent calculus, introduced independently by Mintz, Poitinger, and Avron, comes into this picture. So the reason for the limitations on the subformula property, sequent calculi, is because of the limited expressivity of its structural language of the comma. It's simply the comma and the turnstile. Hypersequents consider multisets of sequence, and therefore it has a more expressive structural language because it has the bar, which is a sequent multiset comma. You could read it. In particular, Chiabattoni et al. Have shown that infinitely many axiomatic extensions of FLE, of FLEC, are sound and complete for hypersequent calculi with the subformula property. In fact, these logics, these hypersequent logics, as I call them here, have syntactic and semantic characterizations, which I won't go into. I do want to show you an example of hypersequent derivation, just to show you how it works. So here is a hypersequent with two components, and then the logical rule, the implication right rule, applies just to a single component, and then the same rule now is applying to the other component. And when you have two components that are identical, as you have here, there is the external contraction rule, which can reduce the two to a single component. Here is the hypersequent calculus for FLEC. You can feel free to pause and have a look if you wish. Right, so let's see how we could extend the arguments of decidability to the hypersequent calculus. First of all, Curry's lemma. We want to show that external weakening, external contraction, and C, let's call this internal contraction, are all height preserving admissible. So one way of attacking the showing height preserving admissibility is to show that the weakening rule is actually not a problem, so it's the contraction rules that we have to worry about, would be to show that we can permute the contraction rules upwards and hence eliminate them from a derivation by pushing them upwards and eliminating them at the top. And that's what you see here, how to permute internal contraction rule, and here is showing you how to permute an external contraction rule. In both cases this works because the premises, the sequent at the top, already contains the duplicates. So in particular it fails when the duplicates have been created in the conclusion or when they come from different premises. So take this example here of the implication left rule. There are 3 copies of A implies B in the conclusion, but one has been created and each of the others comes from one of the premises. So we cannot permute the contraction rule here. So the observation is that permutation may be blocked when there are too few elements in the conclusion. And the solution, which generalizes the sequent proof of Curry's lemma, is to internalize some limited contraction into the conclusion to handle this case. Specifically, if you take this hypersequent rule, take as an example the implication left rule, this is the standard conclusion here. And we replace that with a hypersequent G, which can be obtained from the standard conclusion by applying some limited amount of internal contraction followed by some limited amount of external contraction. To be specific about what I mean by a limited amount of each, it means that there is a G prime, that G goes to G prime by applying contraction rules so that each formula in any component occurs up to K less, and then G prime goes to H where any component in G prime occurs up to L less in H. But neither the formula or the component can disappear because you're always applying contraction rules. You can determine what values of K and L, the minimum values of K and L that suffice, and by replacing all your rules with the rules internalizing contraction in this way, we obtain the height preserving admissibility. That is hypersequent lemma. Next, on to the extended Kripke lemma, where we want to say, given a sequence of hypersequents built using a finite set of formulas, that there exists some element of the sequence such that it can be obtained from a later element by applying internal external contraction or external weakening. So at this point it would be tempting to define the relation simply as being obtainable using these rules. Unfortunately, this is not a partial order, as it is not antisymmetric. You can see this in this extract here, where P, Q, as well as this more complex hypersequent can each be obtained from the other using these rules. To get the partial order, we want to treat such hypersequence as equivalent. This also leads on to the definition of the signature of a hypersequent, which means that for each component in the hypersequent, you look at the formulas that occur on the left, and you look at the formula on the right, and you collect them across all the components, and you obtain, for every hypersequent, you can extract its signature. You define equivalence relation we were talking about before. For technical reasons, weakening is restricted to signature preserving weakenings, but I won't go into the technical details there. And then what we have, if you give me a set of, if you take the set of hypersequents built from this finite set of formulas, we can take the quotient classes under this equivalence relation, and then we define the partial order as we planned to do before. Now suppose I'm given a sequence of hypersequence. I can extract first of all the subsequence, which has the same signature, because there are finitely many options, and we consider the equivalence classes of that sequence. Suppose that there is a descending sequence. We use the infinite Ramsey theorem to extract another descending subsequence where each hypersequent has the singleton signature. And the point is that when we have a hypersequent with a singleton signature, we can associate it with an element of the power set of omega-sized tuples of the natural numbers. We just forget the succeedant B because it's the same in each component. So as a consequence, descending chains in the equivalence classes implies an ascending chain on upward closed subsets of these tuples. Similarly, an anti-chain implies an anti-chain on the upward closed subsets. However, at least since 2001, it is known that such ascending chains do not exist, and there is no anti-chain on the upward closed subsets. And therefore, we conclude that this sequence has no descending chain, and therefore we can obtain the result that there must be an ascending or constant chain, and the result follows. As a side comment, it turns out that the WQO on hypersequence with singleton signature, or equivalently on elements of the power set, appears in the context of domain theory as the Meinering or Smith ordering. And if you look at the right hand side, it's suggestive of the structural rule operations of contraction and weakening that we've been using. Future work. So this work focused on the hypersequent substructural logics extending FLEC. In the case of FLEW, it is mostly unknown, the status of their decidability. The exception is MTL, monoidal T-norm logic, whose decidability was shown by Ono using algebraic semantic argument. But in the large case, decidability is open. And the argument of proof search that we used here does not work because we managed to prohibit ascending sequences of hypersequence using admissibility of the contraction rules. But of course, in FLEW, we don't have internal contraction. So this seems a rather challenging problem. The second question I want to draw your attention to is complexity bounds. Urquhart obtained complexity upper and lower bounds for FLEC roughly matching. In the case of the hypersequent, we can the size of increase of the hypersequent size is controlled because of the rule form. Termination, we saw, ultimately comes down to the minor ring, quasi order. Balasubramaniam has given upper bounds for control bad sequences with respect to disorder, and it's reasonable to imagine upper bound from this argument, following this argument. What would be very interesting is if we can obtain a lower bound for some logic, if it exists within this set of logics that exceeds the primitive recursive bound in the Ackermann function of FLEC. Thank you very much for your attention.